Hello everybody and welcome to the presentation for MobileNVC, where we do real-time neural video compression on a mobile device for 1080p video. My name is Ties van Rozendaal and this is a joint effort with my collaborators, which you can see here on the screen and who I would all like to thank for their contribution. The motivation for working on video compression is easy. There's just a vast amount of video data on the internet, so even if we can improve compression by just a little bit, we can have a big impact. Video compression is a trade-off between bitrate, or the size of the compressed video, and visual quality, and recent advances in neural video codecs have been improving greatly on both axes. However, most of these advances have been coming at the cost of increased model complexity, which is a bad thing if you want to deploy our video codecs to mobile devices. However, very few works have actually focused on model complexity, and there's only one paper that implemented a neural codec on a mobile device. However, this paper only tested their mobile codec on 70p video. And in fact, our goal is real-time decoding for 1080p video of the YOV 420 color space at 30 frames per second or more. I'll first show you how we achieved this goal, then I'll tell you how well our model performs, and finally I'll present some conclusions. We achieved this by implementing and designing a model and an algorithm on the Snapdragon neural signal processor. We start by carefully designing a network architecture, and our MobileNVC architecture is based on the predictive scale space flow model. This model has 3 autoencoders, one for the iframe, the first frame in the sequence, and then there's the p-frame model, which consists of a flow autoencoder, which is used to warp the previous frame, and a residual autoencoder, which operates in pixel space. All of these autoencoders are mean-scale hyperpriors. On top of this, we add a flow extrapolator, which tries to predict the flow based on the last time step for better compression performance. Now, in order to make this model more efficient, we use YOV 420 inputs, and we replace the dense warping with the block-based warping, which is more efficient and also has a lower dimensional motion vector. Then we carefully downscale the networks, especially those on the receiver side, to reach the real-time decoding target. We also reduce the number of warping operations and only use the Y inputs for flow estimation. The block-based warping is an important part of our model design. In contrast, dense warping, which is typically used, has a motion vector for every pixel in the image. However, this does not exploit the fact that motion vectors typically contain large homogeneous regions. Block-based warping actually uses blocks of B by B pixels, and every block shares, within the block, all pixels share a motion vector. This benefits from efficient blockwise memory access, but can have the downside of visual artifacts, especially around the block edges. Overlap block-based warping tries to solve this issue. It is still a block-based warping method with all its benefits, but the artifacts are reduced by using a smoothing kernel based on the neighboring motion vectors. Designing a low-rate, low-complexity model can be tricky, especially because of error accumulation across frames. We tackle this by using a separate loss function for iframes and for p-frames. Since the distortion of later frames is bounded by the quality of previous frames, we use a lower rate loss multiplier for the iframes. Within the p-frames, we do a similar thing with a modulated distortion loss with a higher penalty for later frames. Finally, we use auxiliary losses to let the network better learn how to predict the flow. We use model quantization to integers for efficient low-power inference on the neural signal processor. We quantize the entire model to 8-bit, both weights and activations. We found that some layers in the prior are especially sensitive to quantization and manually fix their quantization grids. Finally, we use quantization in our training to boost the model performance. All of this together is not enough. And we need to deploy pipelined inference to reach our throughput. Again, we run on the Snapdragon 8 generation 2, and this neural signal processor contains different subsystems. So we design a pipeline that uses up to 3 frames, that processes up to 3 frames in parallel in order to use all those subsystems simultaneously. I will now show you step by step how our decoding pipeline looks like. We start by receiving the bit stream and doing parallel entropy decoding on the GPU. We use up to 512 threads in parallel for entropy decoding in order to reach the desired throughput. This gives us the hyperlatence, which we use in the next time step. We pass the hyperlatence through the hyperdecoders, and we also run the flow extrapolator on the neural processing unit. Then we can do another parallel entropy decoding step, again on the GPU. This time the output are the latents. Now we can push the latents through the neural networks, and this gives us the final reconstructed flow and the reconstructed pixel residual. Then, again for the next time step, we can use this flow and the previous frame to warp it in the warping kernel. Then we add the residual to the warped frame on the CPU, and this gives us our final reconstructed frame, which we can then send to the display. So how does our model perform? Well, let's look at some videos. On the top right, you can see some statistics, such as the bitrate for the video and the inference speed in frames per second. If you want to have a better look at the quality of these videos, please use this YouTube link below. Now let's look at the qualitative analysis. Our MobileNVC codec decodes with an average speed of 38.9 frames per second. The plot on the right here shows the compression performance and the model complexity. The yellow dot here is the previous state-of-the-art in on-device neural video compression. The red dot is our model. The x-axis represents the model complexity, where lower is better. We can see that our model uses 10 times less compute than mobile codec. The y-axis shows the compression performance, and lower is again better. And we can see that our model has 48% better compression performance than mobile codec, even though it has less compute. So these are the only two on-device neural codecs as of today. They both have floating point counterparts, which have better compression performance. Then here are some other models which are not designed for on-device inference, and we can see that they have even better compression performance. However, again, these models are not designed for on-device inference. Now let's look at the warping ablation to show the effect of our overlap block-based warping. The baseline is dense warping, which has a motion vector for every pixel, and here we can see the warped frame and the residual. The warped frame looks fine. Now let's look at the block warp. We can see that indeed now the motion vector is divided into blocks instead of pixels. However, we can see artifacts in the warped frame, especially here around the mask pole. This is because the blocks do not align with the pixels. In overlap block-based warping, we can see that these artifacts are fixed. When looking at the compute, we can see that both block-based warping benefit greatly from reduced model compute. In fact, there's more than 4 times less compute operations. Looking at compression performance, here lower numbers are better. We can see that dense warp is only 6% better than our method, despite having more than 4 times more compute operations. Block warping is a lot worse than our method. In conclusion, we are the first to implement a real-time on-device neural video codec for 1080p videos. We use 10 times less compute, but have 48% better compression performance than the previous on-device neural codec. And most neural codecs are still too computationally expensive to be adopted in real-life settings, and we think this presents an interesting direction for future research. Thank you very much for your time and attention, and if you are interested, please check out our paper on arXiv or check out the YouTube link.